I thought I would go over drawing Lewis structures and actually draw them for you the way you're normally accustomed to doing the work yourself. And so let's go over the rules again and let's take a look. All right, so first thing you're going to do is you're going to count the total number of valence electrons in a molecule or ion, and I'll go over how to do that. Identify the central atom, place the other elements around the central atom. That's usually going to be the first element that's in the chemical formula, unless that element is hydrogen, because hydrogen can only make one bond, therefore it can never be a central atom. Place 8 electrons around each element in the structure except for hydrogen, because remember, it can only form one bond. That's only going to be 2 electrons. Count the number of electrons that were placed in the structure. Compare the number of electrons used to the number of electrons that are actually present. If the number of electrons that you actually used to draw the structure is equal to the number of electrons that are actually present in this particular structure, that is the valence electrons, the number of them is the same as the number that you've used to draw the structure, you're done. Your structure's complete. If the number of electrons used is larger than the number of electrons actually present, you have to modify your structure to draw multiple bonds, and we'll go through that several times. If the number of electrons used is smaller than the number of electrons actually present, place the excess electrons on the central atom. And I meant that to be excess electrons on the central atom. And then check, just compare, count them up again, do your comparisons, see if you're done yet. All right, we're going to start out with methane, CH4, the simplest hydrocarbon. First thing you want to do is count up the number of valence electrons. So I look over here at carbon, and it's got 4 valence electrons. So I'm just going to plot my 4 up there. Plus, I have 4 hydrogens. So however many electrons hydrogen has, I'm going to multiply them times 4. There's 1 electron per hydrogen, so that is going to be 4. 4 plus 4 equals 8 valence electrons. All right. Now your central atom is carbon. Remember, hydrogen can never be one, and usually the central atom is the first atom that's in the chemical formula. So I'm going to go ahead, I'm going to put carbon as my central atom, and then I'm just going to take my satellite atoms, the atoms that are around the central atom, and I'm going to plop them up there in a symmetrical way, because that seems like the right way to do it, that they would be symmetrical. Now I'm going to give everybody what they want. Hydrogen only wants 2, but carbon wants 8. We call these Lewis dot structures, so I'm going to make these dots. So I've got 2, 4, 6, 8. I have 8 valence electrons. I used 8 valence electrons. There are 0 left over, and so I'm done. Now normally what we do is we use lines instead of dots once we've got a complete structure, just because the dots are sort of annoying, and so we'll normally draw methane and any other molecule if they've got bonds in them. We normally draw methane or any other molecule using lines to represent the bonds. Every line equals 1 bond, which equals 2 electrons. So these are all single bonds. So that represents a single bond. A single line is a single bond and 2 electrons. So 2, 4, 6, 8. And that is our structure for methane. Now we've got ammonia. This is NH3, ammonia. Technically, it's a weak base. You use it to clean your floors. It's antiseptic. It has a lot of good uses. It's also a precursor for a lot of other nitrogen-containing compounds. And so the first thing I do is count up the number of valence electrons. Here's nitrogen. I go to the top of the group. It has 5 valence electrons. Plus, there are 3 hydrogens. Each of those have 1 valence electron. So 3 times 1 is 3, plus 5, that is 8 valence electrons. My central atom's going to be nitrogen. I'm going to go ahead and just place my hydrogens around in a symmetrical way that seems reasonable. I'm going to give every one of these atoms what they want. Nitrogen wants 8, hydrogen only wants 2. Okay, so you have 2, 4, 6, and 8. And so 2, 4, 6, 8, I used 8, I have 8, there are none left over, so I'm done. So this is ammonia. I'm going to go ahead and draw it with lines. So that's going to be N, and I'll plop the hydrogen down here. That's sort of just tradition. And I'll put this pair of electrons up here. This is what we call a lone pair of electrons. It's also called a non-bonding pair of electrons because this pair of electrons are not making bonds. You might also hear it just say, well, there are 2 non-bonding electrons. So you have to be careful the way they're referred to. And, you have 2 shoes or you have a pair of shoes. You have 2 non-bonding electrons or you have a pair of non-bonding electrons. It all means the same thing. So we've got 2, 4, 6, 8. Our structure is done. This structure has 3 single bonds and it has 1 non-bonding pair of electrons. Okay? And that is ammonia's Lewis dot structure. All right, if you're a biologist, you use this all the time to preserve dead things, if you're that kind of biologist. And this is formaldehyde. So let's go ahead and count the total number of valence electron. Carbon's at the top of the group. Carbon has 4 valence electrons. Oxygen is in group 6. It has 6 valence electrons. There are 2 hydrogens. Each one of those has 1 valence electron. So that's 4 plus 6, that's 10, plus 2 times 1, that's 12 valence electrons. All right. So let's go ahead and find a central atom. That's going to be carbon. I'm going to go ahead and put oxygen up here. And each hydrogen I'm going to put out here. Remember, hydrogen can only make 1 bond, so I couldn't put another hydrogen out here. I'm going to give everybody what they want, which is 8 valence electrons, except for hydrogen, which only wants 2. So that's 2, 4, 6, 2, 4, 6, 8 for carbon. Each hydrogen has 2, 2, 4, 6, 8 for oxygen. And so everybody's happy. Let's count the total number up. 2, 4, 6, 8, 10, 12, 14. Well, I used 14 to draw my structure. I only have 12 in the structure. Nature did not give me 14 electrons to draw this structure, so my structure cannot be correct. So anytime you wind up in this situation, well, not anytime, but most of the time when you wind up in this situation, what you're going to want to do is make an extra bond. And when we make an extra bond, we're going to have to make a double bond in this particular case. All right, so here we go. How do we make a double bond? Well, you can't make a double bond to hydrogen. Hydrogen can only handle 2 electrons. A double bond is going to have 4 electrons. So we're going to take these 2 electrons from carbon. We're going to take these 2 electrons from oxygen. What we're doing with them is we're going to throw them away. So we're throwing away 4 electrons, 2 on carbon and 2 on oxygen. And we're going to replace those 4 non-bonding electrons with 2 bonding electrons. That's a net reduction of 2. We've given up 4 non-bonding electrons. We replace them with 2 bonding electrons. And that is a net reduction of 2. All right, so now let's count up. 2, 4, 6, 8. Carbon is happy. 2, 4, 6, 8. Oxygen is happy. And each hydrogen has 2, so each hydrogen is happy. Now let's count the total number up. 2, 4, 6, 8, 10, 12. So we have 12, we use 12. That is our structure. Let me go ahead and redraw formaldehyde using lines. So we've got a double bond to oxygen, 2 non-bonding pairs of electron on oxygen. I've got hydrogen with single bonds. So I have 2 single bonds, one between each carbon and each hydrogen, and I have 1 double bond, and I have 4 non-bonding electrons, or 2 pairs of non-bonding electrons on the oxygen. 2, 4, 6, 8, 10, 12. Okay, so that is my structure. I have 12, I've used 12, my structure is complete. So whenever you have more electrons in the structure that you draw than you actually have, the first impulse is to go ahead and make double bonds. There'll be some instances where that doesn't occur, but those are rare. Let's do dinitrogen N2. First thing we want to do is count up the number of valence electrons. We've got nitrogen, there's 2 of them, and each nitrogen has 5 valence electrons. So that's 10 valence electrons total, okay? All right, so let's go ahead and draw the structure. There is no central atom. There's no central atom because there's only 2 atoms. And so let's give everybody what they want. Nitrogen, each of them wants 8, 2, 4, 6, and 8, 2, 4, 6, and 8. Okay, so that is, what we've done is we've obeyed the octet rule by giving everybody 8. Okay, so let's go ahead and count them up. 2, 4, 6, 8, 10, 12, 14. Oh my goodness, I've used 14. I only have 10. I'm 4 over. So whatever am I going to do? I need to make 2 more bonds. So let's make 2 more bonds. The first thing I'm going to do is I'm going to remove 4 electrons that aren't making bonds. These are 4 non-bonding electrons. And I'm going to replace them with 2 bonding electrons. Again, that is a net reduction of 2 electrons in my overall structure. I'm now down to 12. 2, 4, 6, 8, 10, 12. I'm going to remove 4 more non-bonding electrons, and I'm going to replace them with 2 bonding electrons. That is, again, a reduction of 2 electrons net. 2, 4, 6, 8, 10. Each nitrogen has 8 valence electrons, and the total number of electrons used in the structure is 10. So I'll redraw this with lines. Here is the triple bond and a pair of non-bonding electrons on each nitrogen. So I have 1 triple bond and I have 2 pairs of non-bonding electrons. What's another way of saying that? I could say I have 2 lone pairs of electrons. Okay, so 2, 4, 6, 8, 10. Total of 10, my structure is done. So a single bond has 2 electrons in it. A double bond has 4 electrons in it that are bonding, and a triple bond has 6 electrons in it. So let's take a look at a clicker question, and let's see if we can't come up with a structure that seems familiar to you. So here is our structure, pH3. I'm going to borrow the periodic table from the previous slide. Phosphorus is in the same group as nitrogen, so it has 5 valence electrons, and then we've got 3 hydrogens. So that's going to be something you're going to want to pay attention to. So we've got 5 valence electrons, and we have 3 times 1 valence electron for a total of 8 valence electrons. Now, phosphorus is going to be the central atom. It's the first element in the formula, so we'll sprinkle it in there. We'll go ahead and throw our hydrogens around. And then we're going to give everything what it wants. I'll go ahead and throw lines on this. Each line represents 2 electrons. And finally, 2, 4, 6, 8. We've got 1 non-bonding pair there. Here's my structure. It has 3 single bonds and 1 lone pair of electrons. So what would the answer be here? Let's see, how many non-bonding pair? Let's see, how many single bonds? Well, that would be 3 single bonds and 1 non-bonding pair. So yes, C is the answer in this case. Now, here's something you might want to take a look at. Look at the central atom. The central atom controls the structure. And look at the central atoms that have 5 valence electrons. It's not just phosphorus, but it's nitrogen, it's arsenic, and it's antimony. They all have the same valence shell electron configuration. So knowing that and remembering that we drew ammonia, which was NH3, and it had a non-bonding pair. If we were to go ahead and draw, let's say, arsine, which arsenic also has 5 valence electrons, we would wind up with this structure. Or stibine with antimony down here, got H, 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 and a non-bonding pair of electrons. Look at that. They all have the same structure, the same Lewis structure. Why? Because they all have the same number of valence electrons for the central atom. The central atom in each case, whether it's nitrogen or phosphorus or arsenic or antimony, they all have 5 valence electrons. They have the same valence shell electron configuration.